Wonderful. Hello, everybody. I'm Steve Brunton. I'm really happy to be here and to tell you about one of my passions, which is nonlinear dynamical systems. So can everybody hear me okay in the back? Yeah, good. So how many of you also love dynamical systems? Good. How many of you aren't sure yet? All right, so I've got 1 hour to convince you the dynamical systems are the coolest. And really, I will say that dynamical systems, nonlinear systems are why most of us are here. So fluid mechanics are one of the original hard dynamical systems. And so this could be an entire course. This could be a year-long course. I'm going to condense down all kinds of interesting stuff into approximately 1 hour. Okay, so this is, pretty shallow. And if you have any questions at all, at any point, please interrupt me. Okay, just like either shout or raise your hand if you have any questions, okay? How many of you have taken a class on dynamical systems? How many have not? It's okay, perfect, good. So I'm gonna talk to both of you. Okay, I'm gonna start off and I have a couple of pieces, and so anything you're interested in, we'll just talk more about. Okay, so dynamical systems, I was thinking about this. Really, any system that evolves or changes in time is a dynamical system. So I always joke with my mechanical engineers that we like time derivatives, DDTs, otherwise we would be civil engineers. Okay, so everything we care about evolves in time, all right? And I'm just gonna give you some examples. I love roller coasters. It was actually hard to find a movie of a roller coaster, but the way I think about the world, dynamical systems are movies. They're not still images, they're movies. They're frames that are evolving according to some physics or some dynamical systems law. We're all here because of fluid flows, in particular unsteady fluid flows, flows that vary in time, okay, and in space. Very high dimensional, nonlinear, multi-scale dynamical systems. In fact, I want to say that again. So the dynamical systems that bring us here today are nonlinear, multi-scale, high-dimensional, okay? Those are really key challenges that we face every day in fluid mechanics. And partly what is interesting about this to me as an applied mathematician is that the same complexity that we have in fluids, we also have in neuroscience. So your brain is a collection of maybe 100 billion neurons that have some very specific connections. They're constantly firing and passing information in time and in space. This is a very high-dimensional, nonlinear, multi-scale dynamical system. Okay, what do I mean by multi-scale? What I mean by multi-scale is that you have your whole brain. Your brain is broken up into regions. Those regions are broken up into smaller regions, and eventually you get down to the cellular level and even the molecular level. And all of those dynamics actually do, in fact, matter to how you think and perceive the world. It's also multi-scale in time. You are listening to the words I'm saying right now over seconds. You're thinking about what you had for lunch, that's minutes. Okay, you're thinking about what you're going to be doing on Saturday. Right? And that, let alone, you're also thinking about months, you're planning years ahead, you have a continuity of self over your entire lifetime. That's extremely multi-scale. You care about fractions of seconds, you care about decades. Okay? And our fluid flow is similarly very multi-scale in space and time. So that's what I mean by multi-scale, is that you care about big scales and you care about little scales, both in space and in time. And that makes it very challenging. It makes it expensive to simulate and to analyze these multi-scale systems. Okay? So other interesting multi-scale systems I think about a lot are disease modeling systems. So I guess, a little bit timely, Bernd. This is an image I got from Josh Proctor, a collaborator of mine at the Institute for Disease Modeling. So if you think about the spread of a disease across a continent, you can think about this in many different ways as a complex, high-dimensional, multi-scale, nonlinear dynamical system. So one way is what is called agent-based modeling, where each human individual is an agent. So maybe there are, about 10 billion states in this system. And then there is a very, very sparse network that's evolving in time of how we're interacting. So for example, us 200 right now are connections in this graph. Okay, and when we go home, that's going to be connecting to other nodes in the graph. And so you have this time varying spread of information across this network. And each node is a nonlinear dynamical system. You have an immune system. You have a behavioral pattern. It's stochastic. It's nonlinear. Okay, very, very complicated. So when I say high dimensional in fluids, does everyone know what I mean? I guess what I mean is that if I wanted to simulate that fluid, I would have to chop up my domain into 1 million or 1 billion grid cells, and then I would be solving 1 million or 1 billion order differential equation. Okay, and that's hard, that's expensive. Okay. In addition, other dynamical systems that are high dimensional nonlinear multiscale are the climate, the atmosphere, ocean dynamics. This is one of my favorite visualizations Philip Dutoit made in his PhD at Caltech with Jerry Marsden. So these are the Lagrangian coherent structure mixing patterns for the entire ocean. This is actually a movie, but each frame took a supercomputer like weeks to compute. Okay, so again, it's very expensive sometimes to compute. And I'll tell you more about what this visualization means later. Okay. Other dynamical systems that are not as complex or high dimensional multi-scale. I mean, this is pretty complex if you think about the rocket and the engine and the combustion, but I'm mostly just thinking about the actual landing of this SpaceX rocket, which is essentially a big inverted pendulum, right? This is a pendulum that's inverted, and they're trying to keep it inverted as they slowly land this back on the launch pad. So this is a classical nonlinear dynamical system that we want to control. Okay, that's one of our chief objectives, is not just to understand systems or to simulate them, but to modify their behavior and control them. So if there was an active feedback control, this would just tip over and crash. Okay? Similar to how I'm walking, actually. I'm an inverted pendulum too. Very unstable. And I think to some extent, you know, a lot of our understanding of physics, classical physics, modern physics, has come from watching the stars. And I actually think this is kind of an interesting image, because if you look at this, you're thinking to yourself, this is just an image. And on our time scales, we don't really see these things moving very much. We see planets moving. We see the stars rotate in our frame of reference. But these, you know, galaxies aren't moving on the time scale of a human life until you look at whether or not they're red shifted or blue shifted. And then you can actually see that there's a tremendous amount of motion in this dynamical system. Okay, so a lot of our understanding and appreciation of science in general has come from astronomy, which is, again, I mean, if you think about it, extremely multi-scale in space and in time. Okay, so I'm harping on some points here. Obviously, I care about things that are nonlinear, high-dimensional, multi-scale. Okay, good. Is everyone motivated? All right, everything you care about is a dynamical system. If you have a dog at home, it's a dynamical system. Okay, so I want to talk about the anatomy of a dynamical system. I think of this as our model for reality. So reality is complicated. We can only model things about it. And we want to model reality at different levels of fidelity. So something I'll talk about in the next lecture on system identification is this idea that you get to, in some sense, choose F to model what you observe. Okay, your measurements of reality. And there's always this dual balance between complexity of your model. Do I model every detail of the system? Do I model the air molecules in this room? Or do I model the bulk properties, the temperature and the pressure? Okay, and so there's always this balance between accuracy and complexity. And what I would love to find is a model that's somewhere in the middle. Okay, so I'm just going to walk through this. X dot equals, how many of you have seen this before? How many have not ever seen something like this? It's okay, good. Just going to go through really briefly. When I write down a dynamical system like this, I'm always thinking about this in terms of the state of the system. The state is the minimal vector of information that I need to describe my system at right now. Okay, so think about a pendulum. So you know that a pendulum has an angle theta. But if I'd only give you theta, do you have enough information to simulate the pendulum forward? No, because if I have this angle theta, I could be swinging through it this way or this way. I need a velocity, theta dot. Okay, so theta dot would be the minimal state of that pendulum system. Okay, so that's what x is a vector of information that you need. F is essentially what we call the dynamics. It is a set of equations or constraints on how x must evolve in time. So that is your system of ordinary differential equations. Okay? Sometimes this comes from Newton's second law. It can come from, conservation of momentum, the Navier-Stokes equation, lots of ways of getting F. In the disease modeling, you could just write down a model, okay, and see if it's good. Now, I'm going to give myself the option of having my dynamics evolve in time. Oftentimes, we're going to have F be a constant function of X. Sometimes F will change with time. Okay, so some examples of that. The climate. The climate dynamical system today is different than it was 50 years ago. The system is being actively forced. It's changing in time. Okay, so things are evolving in time. The dynamics themselves are evolving in time. The economy and finance is a time-varying dynamical system. Okay, the rules today are different than the rules 10 years ago. U is our actuation or our control. So oftentimes, and sometimes we'll get rid of this, sometimes we'll keep this, but in a lot of systems of interest, I have some control knobs that I get to play with to try to manipulate the behavior of my system. Okay? And then beta are going to be all of my parameters of the system. These are the things that I don't necessarily have control over, but they do determine the qualitative behavior of the dynamics, and I'm assuming that they're more or less fixed in time. So it's just a set of parameters that define my system. So like temperature in this room, for example. Okay? Good. Any questions? Okay. So I talked about having access to this state, which is somehow the full state of my system. Now, in my fluid equations, that would be, the velocity and pressure at every single grid cell. So that might be millions or billions of dimensional x. Oftentimes, I don't actually have access to x in the real world. When I'm flying an airplane, I don't actually know exactly what the flow field over my wing is. I only have a few pressure measurements, a few measurements of my system. And so in most cases, I actually only have access to these measurements y. Okay? So I want to walk you through what are some of the key challenges in nonlinear dynamical systems today, in the modern era. So we've been working with dynamical systems for a really long time. Isaac Newton wrote down dynamical systems, nonlinear systems. The modern perspective on dynamical systems is only about 100 years old, starting with Poincaré. Okay, and I'm going to talk about what are the key challenges, maybe in the last 10 or 20 years, that are still problems now. Okay, and I should point out, when I say nonlinear, does everyone know what I mean? Yes? Okay. If I had a linear dynamical system, Bernd knows what I mean, it would be x dot equals a matrix A times x. And we know how to solve matrix systems of equations, right? It's e to the exponentiate A times time. Okay, that would be the solution at forward time. And what linearity means is that if I have two solutions, when I add them, their sum is also a solution. That is not true for nonlinear systems. Superposition doesn't hold. Okay? That's the key takeaway of what nonlinear means. And it means that all of our nice fancy tools go out the window. Okay, so challenges. The first challenge I'm going to point out is that oftentimes F is not known. We don't have equations for your brain. We don't have equations, or we can't agree on equations for the climate. Okay? We don't know what the equations for the coronavirus are. We don't know. So we don't know the dynamics for almost all of the systems we care about. Even the systems we do care about, like the Navier-Stokes equations, we have a beautiful set of equations that very, very accurately describes incompressible fluid flows. but they are too complex to use for everyday design, optimization, and control. Like, try to simulate Navier-Stokes in real time for a scramjet, right? We can't do it. That's why we don't have good scramjets, because we can't do, real-time model-based control. If we could, we would have them. That's oversimplification. That's not true. But so even when we do know F, we need reduced order models that capture the dominant coherent structures, the patterns, the things that actually matter to our engineering objective. And so we need to be able to build these models F from data. So that's probably the key challenge. And it's not talked about that often. We usually assume we have a model F when we start our dynamical systems class. But the systems I care about, I don't have F. Okay? What are some other challenges? Actually, I want you to tell me. What are some challenges of dynamical systems? What do you wrestle with? Noisy measurements. I know you wrestle with that every day. What else? So noisy measurements. Isabel?
Available data streams.
I didn't hear the first word.
Available.
Yeah, so like getting enough data to characterize the system. Bernd?
Finite time horizon.
Okay, finite time horizon. How?
Neighboring, strong causality is not obeyed. So neighboring trajectory can end up completely different ones.
So strong dependence on initial conditions, chaos, uncertainty, amplifying in time. Okay. So does everyone get uncertainty amplifying in time? Like I'm an inverted pendulum. If I go a little to the left, I go a lot to the left. If I go a little to the right, I go a lot to the right. That amplifies in time. Okay. So I've already talked about nonlinearity. Nonlinearity is a huge one. That is what keeps us all in business. Okay, so seriously, you have job security, no matter how young you are, because of nonlinearity. That's why we're all here. If our world was linear, we would go home right now. Okay? I've already talked about high dimensionality. The systems we care about and we're talking about are massively high dimensional and multi-scale. Yeah, good. Chaotic, this is what Bernd talked about. It is, if I have a simulation and I just breathe on that simulation the wrong way, it diverges into a different solution. That's what chaos means. A big one, a really, really big one, is having hidden variables, latent variables that you didn't realize you should have been measuring. And that goes to Isabel's point of available data. Oftentimes, we do our best job designing an experiment. We think we measure everything and control everything, and it turns out that there were some variables we just didn't account for, okay? Or maybe I only have access to certain measurements and I didn't measure the full state X. That's a huge one, okay? Noise and disturbances. This equation was just wrong until I add this plus disturbance, and this equation always has measurement noise. And we always assume that they're white Gaussian, but that's almost never true. Okay, almost never true. And then I think really critically, there is uncertainty in every single piece of this equation. Okay, there is uncertainty in the structure of my ordinary differential equation. There's uncertainty in my measurement of X or of Y. There's uncertainty in the parameters. Maybe my temperature is only good up to plus or minus 0.1 degrees Celsius, because we're here, or Fahrenheit. And maybe that makes a huge difference on your solution. Okay, so understanding and quantifying uncertainty is one of the biggest challenges we have today in dynamical systems. Okay, now something I want to point out, because tomorrow you're going to hear all about machine learning, right? That's why we're here to some extent. And I'm going to tell you about my perspective on machine learning to solve some of these problems in dynamical systems and to solve some of these problems in fluid dynamics. And what I want to point out is that almost every single challenge that I've listed here, and they're not problems, right? Because that would be negative. They're challenges, they're opportunities. I'm not kidding. They're opportunities for you to make your name in your career. These are all opportunities, okay? If someone tells you something is hard and can't be done, go work on it. All of these are optimization problems. In fact, almost every problem in fluid mechanics and dynamical systems and control theory can be written as an optimization problem. And the perspective I'm going to take tomorrow is that essentially machine learning is just optimization based on data. Okay, so these are all things that we can use and leverage modern tools for. Okay? Would anyone like to ask any questions? Is everyone feeling good about this? Okay, good. So why do we actually want this model in the first place? Of course, we want to be able to predict the future, right? We want to be able to simulate our, turbulent flow or our combustion or whatever we're doing and see what it does, how it behaves, does it blow up, right? I want to know. And sometimes actually our dynamical systems, so in chaotic systems and turbulent systems, oftentimes I don't care so much about one individual trajectory. I care about kind of an average trajectory or an ensemble of trajectory, the standard deviation of what my trajectories might do. So I might want a statistical prediction of the future given some uncertainty. Okay, that's key. I want to use this model oftentimes for design or optimization. So if you think about Formula One or rocket engines or yachts, you're going to use these models to accelerate some kind of a design or optimization process. Actually, I think the rocket engine I showed for SpaceX is a really good example. During the space race, when NASA was building rockets, they blew up like 1,000 J-1 rockets, testing the different geometries and combustion chambers and ratio. I mean, it cost $1 trillion in modern dollars. Okay, and they could do it because they had to do it, but we can't afford to do that now. I've talked to engineers at Blue Origin and SpaceX. They can't afford to test 1,000 rocket engines and have them all blow up on the launch pad. So they need better predictive capabilities, better predictive tools about if it will or will not blow up before they blow it up. I mean, it's a really simple distillation. But this could cost $1 trillion or not, depending on the quality of your model. Okay. I personally want to control everything, especially my dynamical system. So control is really important, right? You have your dog's a dynamical system. You tell your dog to sit. You want your dog to sit. Okay, so you're going to train, you're going to control your system. You're going to learn how it responds to your commands, and then you're going to change those commands to get the behavior you want. That requires a pretty good understanding of the system. Okay, it's like psychology. This is dynamical systems psychology, control theory. And at the end of the day, I want to actually understand my system. I don't just want this to be a predictive tool. So a lot of people in machine learning are going to tell you that they have a model of your system because they trained a big, deep neural network, a big black box, okay? And that may very well be useful for future prediction, optimization, and control. We also want to understand our systems, okay? And we want our models to be interpretable, meaning that this F is not so complex or so abstracted that I can't communicate to you what it does. Even the Navier-Stokes equations, which are very complex, I can tell you what they are in one sentence. It's conservation of momentum in a fluid. It's interpretable. It's also very generalizable. I can write down that I can learn that from one set of fluid experiments, and I write it down, and it applies to lots of other cases of fluids that I've never seen before. That's something you want in your models, trust me. Okay? Especially if you're going to do control with those models. Okay, good. That's my spiel. Those are the things I care about in dynamical systems. Those are the things I think that there are hundreds and hundreds of careers in the future on dynamical systems, especially in fluid mechanics. So now I'm just going to tell you all about dynamical systems and examples and fluids and just cool stuff. And again, please interrupt me. So this is a picture that I have adapted from kind of where I learned dynamical systems, which is Guckenheimer and Holmes's textbook, 1983. It's a really good book. Highly recommend it. And so I think about dynamical systems as an increasing progression of nonlinearity and complexity. Okay, so on the left, we have linear systems, which we really kind of perfectly understand. Okay, spring mass systems, small amplitude pendula, periodic oscillators. We know every single thing about these systems. In the middle, what we have is kind of weakly nonlinear systems, where it's not as simple, but it's not chaotic. It's kind of deterministic behavior. And I'm going to tell you about this in a minute, okay? How many of you have seen pictures like this? Phase portraits? Okay, good. And then kind of as you go down this progression of nonlinearity, you start getting into really chaotic systems. These are the ones Bernd was talking about, where if you just look at your initial condition the wrong way, it goes in a completely different direction. Okay, so these are our chaotic systems. I'm going to walk you through some of this progression. Have you learned about linearization in this lecture series? I know that Peter talked about this, the idea that you linearize your equations. I'm just going to walk you through. How many of you have not seen how to linearize a nonlinear system before? Everyone has. A little bit. I'm going to go fast then. So this pendulum is a good example of an actual nonlinear system that we can treat as a linear system in a lot of cases. Okay, so my pendulum, if I have a small amplitude motion, it just does a harmonic oscillator. Okay, that's linear. But if I increase the energy in my pendulum, it starts to act weird. The period changes. The period eventually becomes infinite as I go to the top. Okay, and so it's a fundamentally nonlinear system, but it has two fixed points. Fixed points are states where the dynamics are equal to 0. Okay, and this is really important in fluid mechanics. For example, your laminar boundary layer is often an unstable fixed point. It's a fixed point, but it's unstable. So if you breathe on it, it goes into turbulent boundary layer. Okay, so we're going to take our nonlinear system x dot equals f of x, and we're going to linearize it. We're going to look in, zoom in, near a region around some fixed point x bar where the dynamics are 0. And for the pendulum, the two fixed points are the obvious one where the pendulum is down. When the pendulum's down, it stays down. The other one is where the pendulum is up. And if you could perfectly build your experiment in the pendulum up condition, it would stay there. But it's unstable, obviously. Okay, so those are the two fixed points. And what we're going to do is we're going to say that our state x is some small perturbation delta x around our base state x bar. Okay, so our d delta x dt equation is equal to x dot because x bar is a constant, so d dt of x bar is 0. So x dot equals delta x dot. And that equals f of x plus delta x. And now what we're going to do is we're going to Taylor expand f of x bar plus delta x. This is pretty simple. We're assuming small delta x. And we get f of x bar, which we said was 0 because it's a fixed point, plus the Jacobian derivative of f with respect to x. This is a matrix of partial derivatives, okay, evaluated at your fixed point times delta x, plus higher order terms that are order delta x squared or higher. So if I have small delta x, these are negligibly small. If I have a small zoom in around my fixed point, small angle approximation, I get a linear system given by this linearization. And this Jacobian, when I evaluate it at my fixed point, becomes a matrix A, and I get a linear system. Everyone okay with this? Good. And I can do that about multiple different fixed points. So that's good. I'm just going to go through this pretty quickly. Why linearization in the first place? So why do I want linear systems in the first place? Why do I take my nonlinear system and zoom into linear fixed points?